Let's take a look at superposition and interference. So these two phenomena are examples of when multiple waves interact. Previously, we looked at what happens to a single wave when it, say, goes into a new medium or reflects or whatever. But what happens when two waves come together? Well, superposition is the idea that if two waves overlap in a medium, the displacement of the medium where they overlap is going to be the sum of the displacement of each of the waves. Okay, let's figure out what that means. So let's say we have two wave pulses that are approaching each other. And when I say a wave pulse, this is what I mean. It's just a little bit of a wave. So nothing says that the waves that we look at have to be perfect sine waves, which are the kinds that we've been looking at so far. We can just have a little bit of a wave. It looks like this. That's fine. And we call that a pulse. So let's say we have a pulse that looks like this, and it's traveling to the right. And then we have a pulse that looks like this, and it's traveling to the left, so they're approaching each other. They're going to overlap. What happens? Well, let's think about that. The displacement of the first wave, the little one, will look like this. And the displacement of the second wave will look like this. And that's what it's going to look like when they overlap. Well, the total displacement of the medium is going to be the sum of the displacements from each of the pulses added together. So it'll look like that. This is what it'll look like when the two pulses overlap. All right. Now it can be instructive to look at kind of a fake looking version of a pulse. So let's do that. Let's look at a pulse that looks like this and a pulse that looks like this. They're approaching each other. What happens when they overlap? Okay, well, when they exactly overlap, okay, here's the first pulse, here's the second pulse, and the sum of the two pulses is going to be 0. All right. And now, what happens when they have passed through each other? Well, it turns out when they've passed through each other, they're unaffected. They just keep moving on. So later on, it would look like this. Now let's imagine if we have two pulses that look like this approaching each other, two kind of positive pulses. Well, when they overlap perfectly, the two pulses will add together to make a big pulse. And then afterwards, they pass right on through each other, and they're unaffected by the combination, by the interaction. Now, that situation up here where the two come together and they cancel each other out, we call that destructive interference. And the situation over here where they combine and make a bigger displacement, we call that constructive interference. All right. Now let's look at interference from two sources. So we're going to imagine a situation where we have two sources. Let's call them X and Y. And we're going to say the sources emit coherent waves. What I mean when I say coherent waves is they're waves that have the same wavelength, and they're waves that are in phase when they are emitted. So that means that if source X is emitting a peak at one moment, then source Y must also be emitting a peak at that moment. And if source X is emitting a trough at one moment, then source Y must also be emitting a trough at that moment. All right. So now let's think about a point P. And let's say this point P is equidistant from X and Y. It's the same distance from X and Y. If that's the case, then if point P is receiving a peak from X, then point P must also be receiving a peak from Y. Now, if that's not immediately obvious, and it's okay if it isn't, but if that's not immediately obvious, then think about it a little bit. I'll try to draw a picture of what's happening. But let's say P is receiving a peak from X, then it must also be receiving a peak from Y. That's because it's equidistant from those two sources. Now, likewise, if point P later on, half a period later, is receiving a trough from X, then it must also be receiving a trough from Y. And again, we get constructive interference. No matter what, point P is going to have constructive interference. All right, let's think about another point, point R. Let's say point R is 3 wavelengths away from X, and it's 2 wavelengths away from Y. So my argument is, if point R is receiving a peak from X, it must also be receiving a peak from Y. And try to draw that. Okay, so it's receiving a peak from X, receiving a peak from Y. Okay, that also means that point R, if it's receiving a trough from X, it also must be receiving a trough from Y. The waves that arrive at R are going to be in phase no matter what, which means I'm going to get constructive interference at R. All right, let's keep going. Let's look at a point Q. Now, Q is a little bit different. It's going to be 2 wavelengths away from X and 1.5 wavelengths away from Y. So what that means is if point Q is receiving a peak from X, it must be receiving a trough from Y, because it's 2 wavelengths away from X, 1.5 wavelengths away from Y. And likewise, if point Q is receiving a trough from X, then it will be receiving a peak from Y. No matter what, I'm going to get destructive interference at Q. The waves that arrive at Q are always going to be completely out of phase. So I'll get destructive interference at Q. And then another fourth point, point Q, let's say it's 3 wavelengths away from X and 1.5 wavelengths away from Y. Well, you can guess if I receive a peak from X at S, I'm going to receive a trough from Y. And if I receive a trough from X, I'm going to receive a peak from Y. The waves that arrive at S from the two sources are going to be completely out of phase. And so I'm going to get destructive interference at S. So what matters in these situations when we're talking about interference from two coherent sources? What matters is the path difference. If we kept doing this and looking at multiple points, what we would find is that what matters is this path difference, which is literally the difference in the distance between a location and the two different sources. So if I have a point right here, and I think about the distance to this source and the distance to that source, the path difference is just the difference in the distance to those two sources. And if the path difference is equal to n times the wavelength, where n is an integer equal to 0, 1, 2, and so on, then I get constructive interference. If the path difference is equal to n plus 1/2 times lambda, where n is equal to 0, 1, 2, and so on, then I get destructive interference. The last thing we're going to look at is double slit interference, also called Young's double slit experiment. And in this situation, we're going to imagine that we have two slits, sometimes called apertures. And usually we think about this in terms of light waves. So we're going to have light waves that are incident upon these two slits. When light passes through one of the slits, it's going to diffract. When light passes through the other slit, it will also diffract. So we're going to imagine the light doing that. And then we're going to imagine a screen over on this side. And the light is going to be incident upon the screen. And you can think about different points on the screen. And maybe at this point, right here, maybe it's equidistant from the two slits. So the light coming from each slit is going to impact there. And if it's equidistant, we'd expect the light to constructively interfere. And what that means, if the light is constructively interfering, we're going to get a bright spot. All right, you can imagine a different spot over here. And this has a different distance to each slit. And if it's just right, then if the path difference is such that we get destructive interference, well, then right there we would see a dark spot. And there might be another spot up here where we again get constructive interference, and that would correspond to a bright spot, and so on and so on. And so on the screen, you would see a pattern of alternating bright and dark regions. Sometimes these bright regions are called fringes, but no matter what, we can write down an equation that describes the separation between these bright spots. The bright spots, the separation is given by this. S is equal to lambda d over d. Now, small d in this equation is the distance between the two slits, or apertures. Capital D is the distance from the slits to the screen. Lambda is the wavelength. And S is the distance between the bright fringes on the screen, which is to say, the distance between the points where we have constructive interference on the screen.